Welcome to a new training course focused on mesoscale environment analysis, or MEA. There is growing interest in the role of MEA in severe weather operations. However, we don't have a solid training program on the subject. The individuals listed below were part of a unique team representing 4 CONUS regions and SPC. The team focused on developing advanced level MEA training that supports improved severe convection IDSS. This introductory module focuses on the value of MEA in operations. It will define how unique MEA is, compare 2 different approaches to severe weather operations, assess why radar-based warning decisions can be problematic, assess MEA not only for improving warning decisions when it comes to communicating imminent threats, but also for communicating expected event evolution during the next 1 to 3 hour period. Finally, it will describe the vision of MEA and the end goals for this training initiative. Hi, I'm Pete Wolf, and I'd like to welcome you to this unique training initiative on Mesoscale Environment Analysis, or MEA. During my entire career as a SOO, covering over 2 decades at 2 field offices in 2 different regions, I've been involved in MEA, either directly in operations during high-impact events or teaching forecasters on the subject, so MEA is nothing new. It is gaining interest, likely due to new tools and technologies that support it, such as a new advanced satellite, high-resolution convective allowing models, even greater surface observation coverage than 20 years ago. I have repeatedly seen its value in severe weather operations, either through better warning decisions with longer lead times or better IDSS messaging of event evolution. And that's great, but also consider the personal value of increased job satisfaction that comes from using science to improve operational results. If you issue a warning simply based on the sudden appearance of a radar signature and get a few minutes of lead time, that's good, but it's not very satisfying. What if you could use science to accurately anticipate the event before radar shows the imminent signatures? Wouldn't that be a bit more satisfying? Now, what if you could use science to accurately communicate 1 to 3 hour event evolution, targeting the threat down to the county or even sub-county level, preparing partners well in advance of warning issuances? It is the challenge that MEA offers that brings substantial job satisfaction, using science to make good decisions rather than letting the technology do so for us. There are no MEA requirements in operations. Radar-based warning efforts are sufficient to meet mission objectives. While this training can be helpful to all forecasters, it will likely be most beneficial to those who really want to excel at their work, who believe that good enough is not really good enough. My hope is that this training program offers positive motivation about what you can achieve as a scientist and the satisfaction that success can bring. At the same time, I want you to understand that the reward of MEA comes with risk. Accurate MEA requires full knowledge of the datasets used in environment analysis, correct conceptual models of how the atmosphere works, and the ability to effectively communicate environment information to your team so they make good decisions. After all, IDSS is not just about external decisions, it's about improving internal decisions as well. Let me illustrate the importance of accurate MEA through a simple case example. In March of 2020, an isolated HP supercell developed over southern Georgia in an environment characterized by a moderate level of instability and deep layer shear. Based solely on radar, given increasing low-level rotation on the north side of a well-defined rear flank downdraft, you might go with a tornado warning at this point. However, surface temperatures and dew points were only in the 50s, with very little low-level CAPE. In fact, there was a substantial frontal aversion in place, given a warm front further south over northern Florida. The supercell was tracking along the northern edge of a sharp 0 to 3 kilometer CAPE gradient. The storm only produced strong winds, which knocked down a few trees. Was it simply too cold for a tornado? Not necessarily. In fact, a month earlier in the Mid-Atlantic region, another event occurred, also with surface temperatures and dew points in the 50s. But the vertical temperature profile was different, with no low-level inversion. CAPE values were small, but large enough to promote deep moist convection, and a powerful storm system promoted very strong vertical shear. The result was numerous damage reports, including a few tornadoes. So in addition to the need to focus 3-dimensionally on the environment, These two cases also illustrate the importance of not focusing on specific values of fields like CAPE. The tornadic case here had much lower overall CAPE than the non-tornadic case, but had higher values of CAPE in the lowest 3 kilometers. There are two basic approaches to severe storm operations. First, there's the recipe approach. Here, there's no science needed. What you need is written out for you. This is reactive in nature. You respond to a specific thing with a specific action. This is a safe approach, as the guidelines or requirements are responsible for any errors that result. In contrast, the science approach focuses on predicting, anticipating. Here you have to make decisions, often without supporting guidelines or requirements to back you up. Sometimes you'll be wrong. In the recipe approach, why is that not sufficient when it comes to using radar for warning decisions? The answer is seen in our national verification statistics, which have come down in recent years. Here we see 2-year average covering 2018 and 2019. Even for strong tornadoes on the right, our scores have come down, with lead times down to nearly 10 minutes, and nearly 20% of these events not warned. Are we doing our best by focusing primarily on radar data? In the recipe approach, the radar tells you what action to take. See a moderate or strong rotational signature, issue a tornado warning. In the science approach, radar is used to confirm or adjust expectations. Take a look at the radar animation to the right. It shows a fascinating evolution, with an initial line of storms breaking up into discrete supercells, with dominant left movers north and dominant right ones to the south. The photograph is likely different from north to south across Indiana. Also note another set of somewhat discrete storms behind the initial batch that tries to upscale into a line, the opposite evolution of the initial line of storms. So the difference between the two approaches can mean greater value, not just from our products to customers and partners, but to you in the form of job satisfaction. Consider a scenario in which you're making chocolate chip cookies. The recipe calls for a teaspoon of baking soda. When you discover you have no baking soda, what do? Well, in the recipe approach, you follow the recipe with what you have, likely leading to a poor result. In the science approach, you Google baking soda substitute and utilize baking powder as recommended, likely leading to a successful result. So likewise, for MIA, you wanted to utilize the science approach, to use extra additional information to anticipate and to better understand what the radar is going to show as it is showing it. I'd like to provide a personal example of the value of MIA when it comes to anticipating events and the decisions to be made. It occurred early on in my days in Jacksonville. I don't recall the exact day, thus I have to simulate the radar images here, but I recall the event very well. During the day shift, I was contacted by the emergency manager in Wayne County, Georgia, who was in touch with the school board. They needed to know about whether or not to let school out early. You see, in that part of Georgia, roads are mostly dirt roads, which in thunderstorms become mud roads, not good for school buses. I told the guy that radar did not show much, and our model guidance wasn't excited about the potential for thunderstorms, but we did have a 20% chance for an isolated storm late in the day. Over the next few hours, it looked okay. Shortly afterward, the forecaster I was working with came up to me and pointed out these two narrow bands of pinprick showers that appeared to be moving toward each other. One was likely the East Coast sea breeze. I'm not sure what the other one was. Upon closer look, my heart sank. In a moist, unstable, uncapped environment, the collision of these boundaries was likely going to initiate convection, not over Appling County and certainly not over Glynn County, but, of course, right over Wayne County, the only one I briefed. And with little flow aloft, the storms would move very little, yielding heavy rainfall and potential flooding. So, with my head down in frustration, I called the emergency manager back and indicated that while radar still doesn't show anything, we had noticed a few boundaries that may come together and generate intense thunderstorms over the central part of Wayne County, producing heavy rain and possible flooding over the next hour or two. Sure enough, an hour later, as the boundaries merged, intense storms developed in a band right over central Wayne County. So what could have been an embarrassing failure fortunately ended up a success, anticipating impact before radar showed it. That is what MIA is about. The problem with radar-only decisions is that they can be misleading at times. Here are some examples. The strong wind associated with a Boeing line segment can be underestimated if the flow is directed perpendicular to the beam. Potential tornado signatures with storms close to the radar site may not be seen if the storm is far from the radar, such that the beam overshoots the signatures. Sometimes signatures may not be clear-cut. Does the right image show a weak echo region associated with a developing supercell, or does it show two distant cores, one new and elevated next to one that's mature, that are close together and essentially average together in a wide beam? Radars may also run a little warm or cold, and that might impact interpretation a little, especially if two nearby radars show a given storm a little differently. The radar imagery here clearly suggests a tornadic supercell. Note the environment information on the sounding and hodograph supporting that. But what if the near storm environment sounding actually looked like this, suggesting more of an elevated storm? If we could recognize events solely from radar, wouldn't our verification scores be much better? There is very little coincidence in weather. If radar shows something that doesn't make sense to you, you are misinterpreting something or error exists in what the radar is showing. A thunderstorm does not know its location, the time of year, or time of day, if a warning has been issued for it, or where the ground is for that matter. It's not that smart. A thunderstorm is essentially a function of or a response to its immediate environment of instability, shear, and lift. So if you have an Oklahoma supercell environment in southern Florida, guess what you'll likely end up with in southern Florida? Most likely a supercell event. We had such an event in northeast Florida and southeast Georgia back on December 2nd of 2018 that produced an EF3 tornado that struck this secret submarine base that technically you're not supposed to be able to see because it's secret. Nevertheless, it occurred in a favorable environment. It was actually one of a string of supercells moving across that area. The tornadic storm was supercell number 2 on this radar image. It produced a boundary that you actually can see on the reflectivity pattern here, moving slowly southward with northerly low-level flow to the north of it, rather than southeasterly flow towards the next set of storms. So the low-level shear profile was very different for the subsequent storms. They still had mid-level mesocyclones, but weaker low-level rotation. Thus, we had severe thunderstorm warnings out for the subsequent supercells, rather than having this area under tornado warnings for multiple hours. So, should the task of MIA fall in the lap of SPC or the WFO? The correct answer is yes. There are complementary roles for both SPC and the WFO, with SPC focused on the larger scale, meso-alpha and meso-beta, and the WFO downscaling to the meso-gamma or near storm scale. So here's an example with a day 1 marginal outlook for much of Florida, with the WFO in Miami downscaling it for a particular threat area, covering a couple counties for a couple of hours. This involves using local scale tactical threat assessment and messaging to enhance IDSS through the leveraging of cutting edge science tools, conceptual models, observational, and NWP data sets. This is what MIA is about. Environments can change rapidly in time and space, requiring continuous monitoring. In this February 2020 event in the Mid-Atlantic region, severe storms were initially not expected due to the lack of instability. However, some heating early on and advection of higher temperatures and dew points northward across Virginia toward eastern Maryland created an area of low CAPE with no SIN. A powerful storm system provided lift to initiate moist convection that led to a significant event. In MIA, one must be able to recognize rapid environment change and the resulting change in the end result. Here is another event in June 2020 in northeast Florida, another day with severe storms not forecast. In fact, there was only one storm that formed across all of the northern half of Florida that afternoon, and it turned out to be a monster left mover with up to golf ball size hail and damaging winds. Note the storm structure with a developing B-whir, a 75 dBz core above the freezing level, and anticyclonic rotation aloft. Note the radar is to the north, scanning southward on these images. Sure enough, the nearest sounding showed a good level of instability and an anticyclonically curved hodograph given southeasterly inflow, yielding negative SRH that supported a dominant left mover. These cases illustrate that MIA is not just needed on enhanced, moderate, or high-risk days, but even on days with marginal risk or even general thunder forecast days. There are two areas of focus for MIA: communicating event evolution via our IDSS services and improved warning decisions. Take a look at this forecast for the afternoon. Which one provides better actionable intelligence? There is more detail provided in the bottom example. Here we see a 3 p.m. update as isolated storms develop. Again, the bottom example provides more detail on the where and when to support better decisions. Hopefully you see the difference. The more precise and accurate, the more useful. Neither precision without accuracy nor accuracy without precision are helpful. So how do we do this? How do we promote sustainable, reproducible, repeatable IDSS enhancements? It's through a science foundation, mesoscale analysis. A key focus for warning decisions is using near-storm environment information to enhance lead time. Take this example that marine offices often face. A squall line is heading toward the coast. Now, boats travel at only 6 to 8 knots, so they need more than our typical 10 or 20 minutes lead time to get to port. They need their alert at the time of the left image, an hour at least, before moving offshore. The right image yields no option but to ride the storm out. Perhaps okay for a large boat, but not so much for a small boat. How about for inland warnings? The typical result based on radar is to track the line of storms across a given polygon, and as it approaches the end of it, issue a new downstream polygon. The problem with this is that it provides very little lead time to the western part of the downstream polygon. In the case of a marginal environment where there is uncertainty if the line will remain severe as it exits the polygon, this may be the best route. But if the environment is favorable downstream of the initial polygon, why not issue the downstream polygon sooner to provide more lead time to towns in the western part, as shown on the right image? What do you think is the answer to this question? The correct answer is true and false. It's all a matter of perspective. It all depends on one's needs. If you need to just take immediate shelter at your current location, a 5 or 10 minute lead time is more than sufficient. But if you're not located near a safe place, it may take more time for you to get there. Usually discussions on lead time focus on time for taking shelter. Our current averages, around 8 to 10 minutes for tornado warnings, for example, are quite sufficient for that purpose. In fact, the official definition of warning contains short lead time terms like imminent or occurring. But think for a moment about the decisions to be made prior to that for taking shelter. What value can a 45 or 60 minute lead time provide for those decisions that a 5 or 10 minute lead time likely cannot? Some examples. It would allow me time to finish a task, be it shopping at a store or a task at work, before heading home to shelter with family, rather than having me shelter in place and leaving my family on their own. It would provide the time needed for a hospital or other medical facility to move disabled patients to an appropriate shelter, or a time for an airport to move aircraft on the tarmac back to the terminal so passengers can shelter in the terminal rather than on an aircraft. Both of those efforts take time. It would give extra time for someone in an unsafe mobile home to move to a more sturdy shelter, be it a church, a school, or a mall. It would allow a TV meteorologist time to prepare for a live on-air broadcast rather than being potentially caught off guard. And it would allow government entities the means to move resources in preparation for an event. For example, being able to shut down part of an interstate ahead of an approaching large tornado. That takes time to make happen. So there can be considerable value from this longer lead time beyond simply time to take shelter. This leads to an interesting question. Should that lead time come from the warning itself or from another form of IDSS communication? How might the IDSS forecaster, with the help of the radar person and the mesoanalyst, Provide targeted threat information in advance of warnings. This is an important part of the course. What is the correct answer to this question? I'll pause a moment. I wish the answer was true, but in fact, most of the time, it's false. It would only be true if the data were always accurate, but that is unfortunately not the case. In fact, MIA is challenging and time-consuming, requiring time and effort to do so correctly. Distractions and fatigue from other tasks can risk MIA failure. Here's an example from the SPC mesoanalysis page, which uses the RAP as a first guess. Note point X, for which the CAPE value is around 1,000 joules per kilogram, and 0 to 3 kilometer SRH around 300 meters square per second square. What do these values mean? Actually, a variety of possibilities. Here are 6 soundings configured a little differently, all yielding 1,000 CAPE, but likely yielding different results, from no convection to weak convection to strong low top convection to elevated convection. Likewise, here are 4 hodographs with motion vectors generating an SRH value of 300, but again likely with different end results. Here we see 2 consecutive hourly SPC fields of CAPE on top and SRH on bottom during daytime hours. Focus on the red arrows. From 1 hour to the next, during the day where no rain occurs, CAPE should be steady or rising, yet it drops from central Mississippi to northwestern Alabama, and doesn't change much in southern Alabama despite the presence of significant rainfall. On the SRH plots, focus on northeast Louisiana, where SRH rises suddenly from less than 250 on the lower left image to over 450 the next hour. Are these hourly changes accurate? Now, if the data were always complete and accurate, and our interpretation was always accurate, then MIA would be simple. The effort would shift from the science approach to the recipe approach. When the environment shows this, then just do that. Unfortunately, that's not the case. So it's not sufficient to simply look at plan views of fields like CAPE and SRH. It's not sufficient to assume the data you have are always accurate, especially model output. It's important to look 3-dimensionally to understand what is observed or forecast, and use correct conceptual models to accurately predict how the present will evolve into the short-term future. Therefore, it's important to look at soundings and hodographs and to look 3-dimensionally at a system. And it's important to look at observational data to verify the accuracy of model output. This takes time and effort. It's not something you can shortchange without potential negative results. This advanced level training initiative is designed for motivated meteorologists who want to advance their ability to be proactive in assessing and alerting for weather threats through a greater understanding of convection, convective modes, structures, and how they relate to near-storm environment, and how storms themselves can influence that environment. A full understanding of sounding and hodograph interpretation and the impact of environment modification on the end result. A full understanding of the data sets available, their benefits and limitations. And ultimately an interactive training approach, one that shows rather than tells, one that demonstrates the value of MIA in operations. On the path to becoming a reliable and experienced mesoanalyst, please note that this training initiative is the beginning, it is not the end. Practice, practice, practice is needed. Years of practice needed to build experience. So this training is about using science to anticipate rather than to react to high-impact events. Learning how to provide critical near-storm environment information to help your team, be it through your IDSS person to make better decisions in communicating event evolution to partners, or your warning person in making better warning decisions sooner. Now, our focus in this training initiative is on the severe convection program, but it's equally applicable to flood, winter storm, fire, weather, and even the tropical programs. The conceptual models may be different, but the approach to doing MIA is identical. For this initiative, the MIA vision is to have a set of MIA experts at the WFOs who provide critical support to enhance high-impact products and services. The mission of this training initiative is to provide a meaningful interactive training program that provides or enhances a participant's ability to improve high-impact operations through the injection of critical real-time environment information. Our end goal for your office is, of course, to improve the level of services provided, better event evolution information, particularly a few hours before an expected event, thus improved IDSS, and better convective warning decisions that support longer lead time and fewer missed events. For you specifically, our goal is for you to become an effective mesoanalyst for your WFO during high-impact events, supporting proactive rather than reactive decisions, and from that, gaining real job satisfaction. The MIA course is divided into multiple parts, as shown on the MIA course page, which can be accessed through the MIA course curriculum in the CLC. At the top of the page is the introductory video you are currently viewing. This is the first module of the course. Below that is Part 1 of the course, which consists of 21 science assessments, with 5 to 7 questions on each of the 21 topics. The assessments are not graded and no scores are given. It's simply provided for the forecaster's benefit, to assess initial knowledge level before digging into the meat of the course. Training resources are provided for those who feel weak on a particular topic or who struggle with an assessment. You are encouraged to go through the assessments and review the training resources for any topic you need more information about. This should take about an hour to complete, plus additional time for any training resources you wish to explore further. Part 2 is the meat of the course. It consists of 25 modules, broken down into 3 sections. MIA Tools and Technologies covers the variety of tools for the mesoanalyst, including their benefits and limitations. MIA Operations focuses on different hazard conceptual models, MIA Operational Workflow, assessment of risk, and so forth. MIA Communication focuses on both internal communication between the mesoanalyst and the warning team, as well as communication between the warning team and partners, utilizing information provided by the mesoanalyst. On this page, you can differentiate between the very short modules and the longer ones. For ones that are an hour or longer, you are encouraged to take breaks at times rather than trying to complete the entire module in one sitting. Part 2 will likely take 12 to 15 hours to complete. A key aspect of learning is applying the concept you learn, so Part 3 provides a number of case exercises for you to complete. You can complete those cases you wish to do or that are assigned to you by your SUE. Finally, there is a final assessment for the MIA course that you can access through the CLC. This is the only assessment in the course that is graded. It's a 50 multiple choice question assessment with 2 points for each question, requiring a score of at least 80 to pass. This assessment provides a few questions for each of the Part 2 modules. Here's a summary of the key points of this module. Mesoscale environment analysis in severe weather operations is not a new concept, but rather one given a boost from new tools, techniques, and technologies. Unlike the recipe approach, by which radar indicates what actions to take and when, often with little lead time, MIA focuses on the science approach, more proactive and predictive effort to generate a better end result with considerably greater lead time. Understanding near-storm environment can support better threat and event evolution information for core partners and the public through improved messaging for the upcoming 1 to 3 hour period, as well as better warning decisions supporting longer lead times. This training initiative aims to support the spin-up of highly trained mesoanalysts at each WFO to achieve the desired end result. So, if a thunderstorm is a response to its immediate environment of instability, shear, and lift, then if you can correctly understand that environment, you have a leg up on the radar. The value of this is not just the greater accuracy and lead time you can provide to customers and partners, it's also the greater personal job satisfaction you can gain by using science to accurately anticipate hazards and support more lead time as a result. I hope you find this training course to be beneficial on your path to helping your office so that MEA doesn't end up MIA. The next slide will start a short informal learning assessment for this particular module. This, like all of the short module-based learning assessments, is provided for your benefit. If you answer the questions correctly, move on to the next item in the course. If not, I encourage you to review the module or training resources associated with it and retake the assessment. Keep in mind that completing this training is the beginning step, not the end. Practice, practice, practice is important for building expertise. So learning this material and practicing what you've learned through real-time or archived events are important steps to becoming a successful operational mesoanalyst and gaining the satisfaction that event success can bring. For this learning assessment, you will get 6 questions. Each question slide will be followed by the answer slide for that question. As needed, pause the video as you try to come up with your answer. Record it on a piece of paper. Then continue the video to reveal the answer to each question. Good luck.